Dear students, in this lecture, I am going to introduce a new current term called displacement current. It was actually introduced by Maxwell in order to avoid the inconsistency of Ampere's circuital theorem for time-varying conditions. So we will start our discussion with the equation of continuity for both steady state and time-varying conditions. And then we will introduce the displacement current, the expression for displacement current. Then we will explain the nature of displacement current by making the example of a parallel plate capacitor. First, let us consider the equation of continuity for steady currents. I think you are quite familiar with this equation of continuity, even though for getting a smooth start, I would like to explain that once again. And as an example, let us consider a section of the current, a steady current carrying conductor like this, a current density J. A steady current density J is flowing through this section of the current carrying conductor, and a small volume is taken, volume inside the conductor is taken, and the charge density inside this volume is characterized by a rho, that is charge per unit volume. And the equation of continuity for the steady state, the integral form may be written like this, that is surface integral J dot ds is equal to 0 for the selected volume. That is the total normal component of the current over the surface, over the area of the surface, that is J dot ds is equal to 0. And in this case, we can see that the total number of charges entering into the volume is equal to that leaving. That is why surface integral J dot ds is equal to 0. Otherwise, if the total number entering is not equal to that leaving, then surface integral J dot ds is not equal to 0. So we have to consider, for example, if 100 charges are entering into the volume and 80 charges are leaving, that means after that small time, 20 charges are excess there. So in that case, it is not steady state. If 100 charges are entering, then and 100 charges are leaving, then the total surface integral J dot ds becomes 0 in that case. Now let us convert the surface integral into an volume integral using Gauss divergence theorem. So volume integral del dot J dv is equal to 0. So removing this volume integral term, since the right hand side is equal to 0, simply we are able to write like this, del dot J is equal to 0, and that is the differential form of equation of continuity for steady state. Coming to the time varying case, that is equation of continuity for time varying conditions, we can select the same figure with slight modification. The modification in the sense the current flowing through this, that is J, is not static for this case. It is changing with respect to time. That is J. J is a function of time. The earlier case it is not there. J is constant. Always it is constant, but it is changing right now. So that the equation changes to this form, that is surface integral J dot ds, that is the total normal component of J over this closed surface, that is total current over the closed surface, is not equal to 0, because there is, so initially suppose there are 100 charges. After dt seconds that changes to 90. That means there is a minus dou by dou t of the total charge volume integral rho dv is there. The volume integral rho dv is the total charge present at any moment, and after dt second it is changing. It may be reducing or it may be increasing. We are taking it for the present case, we are taking it as a reducing quantity. So we will put a minus sign here, minus dou by dou t of volume integral rho dv, and it is the integral form of the time varying equations. And as usual, converting the surface integral into a volume integral. So using Gauss divergence theorem, so volume integral del dot J dv becomes minus dou by dou t of volume integral rho dv. So removing this volume integral term from both sides, we get it as So again, we are modifying like this: minus volume integral dou rho by dou t dv, or removing the volume integral term, this becomes del dot j is equal to minus dou rho by dou t, and it is the differential form of the equation of continuity for time varying cases. And we are using this time varying equation of continuity for introducing the displacement current. Okay, so we will start with the equation of continuity for time varying cases, and we will modify that equation using Gauss flux theorem. And then we are able to obtain an expression for a new current term, and we will call that as the displacement current term. So del dot T is equal to minus dou rho by dou t. By Gauss flux theorem, we have rho is equal to del dot d. That is, del dot d is equal to rho, or del dot t is equal to rho by epsilon 0. Okay, so substituting this del dot d in place of rho, so that this equation changes to del dot j is equal to minus dou by dou t of del dot d, or del dot j is equal to minus del dot dou d by dou t. So this equation changes to this form: del dot j is equal to minus del dot dou d by dou t, and taking this part to the left hand side, that is del dot j plus dou d by dou t is equal to 0. And taking this part or these terms inside the bracket as j dash, that is del dot j dash is equal to 0. That is del dot j plus dou d by dou t. So j dash is equal to j plus dou d by dou t. So del dot j dash is equal to 0 is similar to that equation for the steady current. For the steady current, we have del dot j is equal to 0, and here it is del dot j dash is equal to 0. So for time varying cases, we have j dash is equal to j plus dou d by dou t, and the second part dou d by dou t. Actually, dou d by dou t is the time rate of change of the electric flux d, or d is equal to epsilon e. So d by dt of the electric field, that is the rate of change of the electric field, and this is there inside the current section, that is j plus dou d by dou t. That is similar to the equation of continuity, that del dot j is equal to 0. So the second term is called a new term called displacement current density. The first term is called jc, the same current j, same term j is taken here as jc, that is the conduction current density, or current due to actual movement of charge carriers through the wires or through a conductor, that is conduction current density. Similarly, JD is called the displacement current density, that is due to produced by a time rate of change of the electric flux. So right now we may write this as JD is equal to dou d by dou t, or epsilon dou e by dou t, as the expression for the displacement current density, and the expression for displacement current ID is simply current density into area. So we are multiplying the density with area of the current carrying section, so, or the field region, area of the field region. So A into dou d by dou t, that is equal to epsilon A into dou e by dou t, or epsilon dou by dou t of A dot E, and epsilon, what is A dot E? A dot E is the normal component of E with respect to the area A, normal component of E, that is electric field quantity in the direction of area. So that is nothing but the flux of E. So phi E, epsilon dou by dou t of phi E. So the expression for displacement current is the displacement current density JD into A, and that is given by A into dou d by dou t, or epsilon A into dou e by dou t, or epsilon dou by dou t of phi E. So the current component due to time rate of change of field is called displacement current. Okay, and the expression is given by dou d by dou t. In order to explain the nature of this displacement current, let us choose the example of a capacitor, a parallel plate capacitor. And let us consider the charging process of the parallel plate capacitor. During the charging process, we can see that charges accumulates on both sides of the parallel plate capacitor. And during that process of charging, the electric field inside the capacitor gradually increases from 0 to a maximum. So dou by dou t of E is increasing from 0 to a maximum. So the electric field inside, or the rate of change of electric field inside, is related to the charging or a change of the conduction current outside the capacitor, that is through the lead wires of the capacitor. Conduction current is approaching, and we are going to relate the conduction current outside the lead wires to the displacement current inside the capacitor, and we may be able to show that the conduction current in that case is equal to the displacement current inside the capacitor. So an example, the charging the capacitor, charged capacitor, is pictorially represented here with the conduction current IC. Okay, IC on both sides will be equal during the process of charging, and that produces plus Q on one lead and minus Q on the other, one plate and minus Q on the other plate, and the electric field E inside changes from 0 to a maximum during the process of charging. And the electric field is given by the famous expression E is equal to sigma by epsilon 0, and it is equal to sigma is nothing but Q by A, so Q by epsilon 0 A, that is the electric field. Now the the rate of change of the electric field, dou E by dou T, dou E by dou T is obtained by differentiating this expression, so that we get it as 1 by epsilon 0 into dq by dt. Now dq by dt is the conduction current. The conduction current responsible for the accumulation of the charges on the plates of the capacitor. So IC by epsilon 0 A. Now substituting this value in the expression for ID. ID is equal to epsilon 0 A into dou E by dou T. Okay, so in the case of inside the capacitor, if there is no dielectric present, it is called epsilon 0. Otherwise, we have to substitute as epsilon A dou E by dou T. So it is epsilon 0 A into dou E by dou T. Instead of dou E by dou T, we are substituting IC by epsilon 0 A. So cancelling this epsilon 0 A from both sides, we get it as IC itself. Okay, so ID changes to IC, and this is the a relation, final expression, that is the displacement current generated inside the parallel plate capacitor is equal to the conduction current flowing through the lead wires of the capacitor during the charging process of the capacitor. Now let us approach the same problem by making use of Ampere's circuital theorem, and for that we are using closed line integral B dot dl is equal to mu 0 times I. Okay, so the picture for that particular case is shown with the two ammeters on the left side and right side, same ammeters, and during the process of charging we can see that the same current is shown by both ammeters, and we can see that there is nothing inside the capacitor, there is no conductor inside. So it is not possible for the conduction current IC in the left side of the capacitor to travel or to transfer to the right side. Actual movement of charge carriers is not there, but it is moving to the other side by some other means, and we are able to show that it is by making use of the displacement current. Now let us take the Ampere's circuital theorem for this path. Closed line integral B dot dl is equal to mu 0 times surface integral J dot ds, and we are evaluating B dot dl for this closed path, closed line integral B dot dl. And first let us take a closed surface, a surface S1 enclosed by this closed path, closed line integral path. Okay, and we will evaluate. And right now we are able to show that a current IC is flowing for this case, And again consider another surface like this, that is surface S2. And here the surface S2 is through the capacitor, so that there is no actual current conductor present. So this figure may be redrawn like this. For S1 we have the current conductor IC is crossing at this point, whereas for the second S2 we can see that it is passing through the capacitor, so there is no conduction current enclosed or passing through the surface S2. So by making use of these two surfaces, we are able to show that ID is equal to IC, that is displacement current inside the capacitor is equal to the conduction current in the lead wires using Ampere's theorem. This is the proof. This type of two surfaces are taken, and we will evaluate the Ampere's theorem to prove this result. First, let us take the first surface, that is S1. For the surface S1, JC dot ds, that is for the surface S1, we can have this part as S1 of JC dot ds, and that is equal to IC. We are evaluating the right hand side of this Ampere's circuital theorem, and so we get it as line integral B dot dl is equal to mu 0 times IC. Okay, so this evaluation is for the surface S1. Now again do the same procedure by making use of this second surface S2. For S2 we have no IC there or JC there, so it is S2 JD dot ds is there. S2 integral JD dot ds. JD surface integral JD means ID. S2 JD dot ds means JD into surface integral ds, that is the area of the capacitor. So JD into area, and that is nothing but ID. Okay, so we get line integral P dot dl is equal to mu 0 times ID. This is the second expression. So comparing equation 1 and 2, the left hand sides are same. Line integral P dot dl is evaluated for the same loop, and the right hand side we get mu 0 IC is equal to mu 0 ID. So that proves that IC is equal to ID. Now one numerical example, a parallel plate capacitor with the circular plates of radius 4 cm is charged with a change in electric field of 10 power 10 volt per meter second. Calculate the displacement current. It's a very simple example. And here this ID, the expression is ID. We are asked to find the displacement current ID. ID is equal to epsilon 0A into dou E by dou T, and the value of epsilon 0 is substituted. Then area is equal to, it is a circular plate with the radius 4. So pi r square changes to pi into 4 into 10 raised to minus 2 meter, pi r square into dou E by dou T. Dou E by dou T is 10 power 10, that is the electric field change is 10 power 10 volt per meter. So that is the rate of change of electric field. And when we substitute, we get it as it is equal to 0.45 milliampere. So it is a very simple method for evaluating the displacement current of a parallel plate capacitor. So we have introduced the displacement current term starting with the equation of continuity, and verified or obtained expressions for the displacement current and displacement current density, and the physical meaning of this displacement current is explained by making the example of a parallel plate capacitor, and we have obtained or derived expressions for the displacement current, or verified this the condition that the displacement current is equal to the conduction current for the example of a capacitor by simply taking the charge concentration on both plates, and also by taking the Ampere's circuital theorem. Okay, so this is very much useful in the case of solving different types of problems related to displacement current situations. And by making use of this displacement current, Maxwell modified Ampere's circuital theorem, and that leads to the famous relation, Maxwell's relations. And the Maxwell relations, we know that these Maxwell's relations are the basics of the entire electrodynamics or electromagnetic wave theory. Okay, thank you very much.